Hey guys, it's Professor Janacek. Want to talk about a convergence test today. Want to look at the geometric series test. We'll have to remember what the geometric series looks like. First, it's based off of the geometric sequence. The geometric sequence has a first term, which we call A, so that's our first term. And then the nth term is r times a sub n minus 1. So remember, this is the nth term, but it's defined off of r times this a sub n minus 1. Recall, this is the term before. So let's take a look at now the series. Remember, the series is the summation. The geometric series is the sum as k goes from 1 to infinity of a times r to the k minus 1. It can also be written as the sum as k goes from 0 to infinity of a times r to the k. So we're going to have to recognize this. This is what it's going to look like when it's given to us. It could start at k and the exponent would be k minus 1. I'm sorry, it could start at 1, the exponent would be k minus 1, or it could start at 0 and the exponent would be k. So we'll have to recognize what that looks like. Once we recognize it, turns out that this is equal to a over 1 minus r as long as the absolute value of r is less than 1. If this is the case, then we say it converges. However, this series diverges if the absolute value of r is greater than or equal to 1. So it turns out all we're going to have to do is identify a, identify r. If r is less than 1, it converges, and we know what it converges to. But if the absolute value of r is greater than or equal to 1, then it diverges. Let's try some examples. Let's take a look at the sum as k goes from 1 to infinity of 9 raised to the negative k plus 2 times 4 to the k plus 1. Now the first thing I recognize is that this one is beginning at 1. So if it begins at 1, we want the exponent to be k minus 1. So we're going to have to do a little work to get that exponent into the k minus 1 form. Right now my exponents are negative k plus 2 and k plus 1. Not at all what we want. So let's do a little arithmetic fun. Let's see, I can rewrite this as negative k, this first exponent, negative k plus 1 plus 1. The exponent on the 4 I can write as k minus 1 plus 2. Right, those should now be the same. Let's see, so this is 9 to the negative k plus 1 times 9 to the 1. The 4 we can write as 4 to the k minus 1 and 4 squared. Not quite there, but we're getting close. This is the sum as k goes from 1 to infinity of 9 raised to the negative 1 times k minus 1. Ah, there it is. There's the k minus 1. And of course, I still have 9 to the first, which is just 9. And this one we have 4 to the k minus 1. That's what I want. 4 squared we can write as 16. All right, so a few more things we could do just to clean this up before we're ready to determine convergence or divergence. Let's see, we have 9. Let me just move the 9 and the 16 here to the front. Then we have 9 to the negative 1 raised to the k minus 1. And we have 4 raised to the k minus 1. All right, well, let's see. 9 times 16. We can do that in multiplication. I think that's 144. 9 to the negative 1, remember that really goes to the denominator. So this is 1 over 9 to the k minus 1. And since these have the same exponent, k minus 1, I can actually put them together. So we have 144 times 4 over 9 raised to the k minus 1. And that's exactly what we want. You'll notice it does have that geometric series form. In fact, it's the first form, this one right here. And I also recognize in this case that A is 144 and R is 4/9. Furthermore, I know that the absolute value of R, absolute value of 4/9, is greater than 1. I'm sorry, how about less than 1? All right, well, if it's less than 1, that tells me that this converges. Furthermore, I know it converges to A, which is 144, over 1 minus R, which is 4/9. So 144 over 1 minus 4/9. We can simplify that a bit. We end up with 1,293 over 5, and it converges. So not only do we know that this converges, but we know what it converges to. Now recognize we don't always know what series converge to, but we can usually determine if they converge or not. Excellent. Let's try another example. Let's take the sum as k goes from 0 to infinity of -4 raised to the 3k over 5 to the k minus 1. You'll notice in this case I'm beginning at 0. If I go back and look at my original information, if I start at 0, then I want the exponent to be k, not k minus 1. All right, so let's see. In the numerator, I have -4 to the 3rd, and then that's raised to the k power. In the denominator, I can write this as 5 to the k times 5 to the -1. So let's see, what do we have here? -4 to the 3rd power, that's -64 raised to the k. In the denominator, we have 5 to the k, but remember 5 to the -1 actually moves up to the numerator, so we have 5 there in the front. All right, we can put some of this stuff together. K goes from 0 to infinity of, notice the -64 and the 5 are both raised to the k power, so I can put them together. That 5 in the back, I'm going to go ahead and move to the front. And so I have 5 times -64 over 5 to the k, and look at that. This is geometric. And I recognize that A is 5 in this case. R is -64 over 5, so that means the absolute value of R, absolute value of -64 over 5, gives me 64 over 5, which is greater than 1, so that means this one diverges.